Hi, everyone. It gives me great pleasure to invite you all to our continuing monthly Inference Colloquium series. These talks, followed by discussion sessions the next day, are part of our larger intellectual project on trying to understand the nature of causation, correlation, and inference across disciplines. Our series, as many of you may know, has comprised talks by eminent scholars whose domains of expertise span physics, philosophy of science, mathematics, and including in the coming months talks by a biologist, an organizational behavior expert, and a computer scientist. The goals of our project are to really understand how we infer from models, the power and the limits of models as inferential engines. And I'm really excited that today's speaker is the philosopher of science whose work is centered on physics, Dr. Elise Crull, whose talk is titled No Cause for Concern, Indefinite Causal Ordering as a Tool for Understanding Entanglement. And I'm delighted that our conversant with Dr. Krull tomorrow's discussion session is the eminent philosopher of science, Professor Yemima Ben Menahem from the Department of Philosophy, the Hebrew University of Jerusalem. We are absolutely delighted to have both of them participate in the sequence of events. But before we start today's presentation, and I introduce Dr. Krull, I would like to recognize our benefactors, Mr. and Mrs. Richard and Barbara Franke, whose generosity in setting up this unique interdisciplinary program and many other activities at Yale have greatly enriched the campus and the university's mission. Also, I need to remind those of you who are assembled here today that we are recording this event and that all participants must therefore mute their videos. And as per usual, please feel free to submit questions through the chat feature for the Q&A session at the end of the talk. Now, to introduce Professor Elise Crull, who is a faculty member at the Department of Philosophy in the City University of New York. After studying physics and astronomy at Calvin University, a very robust and good intellectual background, I might add. I'm joking, of course. I say this as an astrophysicist myself. That Professor Krull took the plunge into interdisciplinary waters, earning both an MA and a PhD in the history and philosophy of science from the University of Notre Dame. Before coming to CUNY in 2014, she held postdoctoral positions at the University of Aberdeen and at the Hebrew University's Edelstein Center for History and Philosophy of Science, Technology, and Medicine, where she spent many blissful hours huddled over documents in the Einstein archives. Oh gosh, I'm envious. While most of her research to date concerns historical and philosophical foundations of quantum mechanics, Krull is also drawn to questions in sort of this hinterland between contemporary metaphysics and physics. These are the really profound and complex questions that have been very, very hard to even methodologically approach. And Elise has made enormous headway in many of these important questions. In particular, she's interested in the philosophical implications of entanglement and quantum decoherence, how these phenomena modify traditional views about the structure of space-time, and what explanatory roles they might play within various approaches to an emerging theory of quantum gravity. So without further ado, Elise, the floor is yours.
How does everything look?
Looks great.
Fantastic. Well, thank you for that generous introduction, Priya, and thank you for the invitation also, Priya and Tai, to be a part of this really wonderful, very deeply and genuinely interdisciplinary colloquium on inference and causation. And I also want to say thank you to the Franks just for their center, such scholarship, encouraging it among undergraduates and graduates and faculty is it's just like the beating heart of the academy, I think. So thank you for your endeavors to create these sorts of spaces for us. So today I'll be speaking about the lack of causality or indefiniteness in causality, hence no cause for concern. I've subtitled it Indefinite Causal Ordering as a Tool for Understanding Entanglement, but I'll in fact be saying something a little bit broader than that, not just about understanding entanglement, where I'll make some provisional gestures, but really just thinking about indefinite causal ordering of quantum processes carefully and understanding what this new physics might how it might inform various discussions in quantum information, quantum computation, quantum gravity, non-relativistic quantum mechanics, and of course in philosophy of physics. So let's dive in. Okay. And apologies in advance if my cat wanders by. He just loves entanglement. So I would like to begin by setting the stage, just giving you a quick sneak peek of one small part of a vast philosophical literature on causation. And then by giving you a sneak peek of the discussion that's happening around causality in physics, just a little bit. And then I'll give you a plan for the talk, and we'll go on. So here is just the brief setup. Now, Matthias Frisch has just, in the last, I think, 10 months, written a Stanford Encyclopedia of Philosophy entry on causation in physics. And I highly recommend it. I believe there's a link on the website to his article. And it's just a very clear taxonomy of the problems and discussions and debates through history. But one thing he does, which is really nice, is characterize the causation discussion in philosophy as being groups of projects that may have overlapping but a little bit separable aims. So there are metaphysical projects that want to think about causation and what it implies about the way the world really is. And what is cause? What does cause mean about spatial temporal relations? What level in the ontological hierarchy should causal processes exist in, and so on. There are also descriptive and sort of descriptive projects that want to understand what is it that physicists are actually doing when they invoke cause or causal processes or causal laws in particular theories. And then there's also the functional aim. How does cause help us make inferences? How does cause help us link up different phenomena, regimes of phenomena, and so on? So that's a quick parsing of the philosophical space. And Yamima has written a lovely book that came out a couple of years ago called Causation in Science. And she is not primarily concerned with the metaphysical project, I believe. But we'll let her say more about that tomorrow. I will be today thinking as a first way in about metaphysics. Right? And in this direction, there are sort of three camps, right? And here they are listed. There are causal fundamentalists. I know we get sort of skeeved out by the word fundamentalist, but here it just means that causal laws are a fundamental part of the universe. So if we find some grand unifying theory, whatever law sits in that theory as sort of the basic law will be a causal law. Or it could be a thesis that says there exists some universal causal principle. And this was historically motivated for a lot of reasons, because we look at the world around us, it seems that events are causally related to one another. And how do we do science? We do science by exploring such connections or such relations. So these two theses come out of a classical understanding of the world. But in recent times, there have been these other views, namely the causal limitivist view, which was maybe made most famous by John Norton in the last few decades. And causal limitativism is just a denial of fundamentalism. They say, look, there is no fundamental causal principle. Maybe cause pops in here and there in our descriptions, or it's a functional tool that we use to build our theories and make predictions and so on, but it isn't a part of the actual structure of the world. So Norton wants to go even further than just eliminating cause from the bottom level. He wants to say that cause only ever appears in a sort of emergent fashion, and where it appears, when we are using that term cause, it can always be reduced. Whatever law or relationship is being described with that term can be reduced to a law or relationship that is fundamentally non-causal. In other words, what looks like causal at the operational or functional level disappears or reduces into something that is ultimately non-causal, right? So causal limitivists, let's eliminate cause. Right? It's a pretty strong position. Somewhere between the last two camps are the non-fundamentalists, and if you're philosophers, you've heard about the Humean controversy, right? The Humeans tend to be the non-fundamentalists, and they deny that both of the theses that there exists a universal causal principle, and they also want to say that causal laws do not exist as part of the fundamental gnomic structure or law-like structure of the universe. But they're going to disagree with the Limitivist too by saying that causal structures or causal talk can still play robust or genuine roles in explaining, or maybe there are some views where causality does properly emerge at some higher level of your ontology, but it isn't at the fundamental level. The fundamental level is just a Humean mosaic, if you will. So those are the three camps, and I'll be looking at the physics and then sort of asking what the physics has to say, maybe about these three camps, if it informs our discussion in any way. All right, so what's the discussion over in physics? There are a few types of responses crudely categorized once again. Of course, causal assumptions are crucial for classical modeling and in classical theories, but it's been understood for quite some time that quantum mechanics allows for non-causal situations. Whether non-causal is equivalent to acausal or just indefinite causally ordered situations will be a question we ask later on. But there are a variety of approaches, right? There are those theorists usually who say, look, yes, it's possible that there is a lack of causal structure, or there's some kind of indefinite causal ordering, ICO, that exists at the bottom level in our quantum theories or whatever. But nevertheless, what this should inspire us to do is to develop causally neutral quantum formalisms, or on the other hand, develop measures for how non-causal certain structures are, right? So maybe this is just a way of saying we should divorce our quantum formalism from the assumption of a background space-time or a background causal apparatus of some sort. So I believe that like Hartree-Field's causally neutral formalism is sort of that vein. Another formal response would be, okay, so at the bottom level, we have indefinite causal ordering, but perhaps there are formalisms we can develop or tools we can develop that allow us to recover causal structure. And that also is being done, for instance, by Kostas and Shrapnel, who developed a causal Markovian condition for quantum systems. So these people are less interested in the metaphysical question of why we don't see cause at the bottom level, or should we be seeing it, or whatever, and are just saying, okay, given that we have the possibility of weird causal situations from quantum mechanics, how can we adjust the framework or the formalism up here so that we can go on with our modeling tasks or enhance our modeling tasks? There has been an experimental response, some of which is to say, okay, this lack of causal ordering can be a way for us to increase efficiency in quantum computation or information technology or information theory or quantum communications, right? And this has already been done. And I'll discuss a paper where indefinite causal ordering has in fact more efficiently allowed for the computation of some specific problem, as opposed to a causally ordered superposition of a quantum circuit. Okay. There's also a theoretical response that says, well, let's look at this lack of causal ordering and use it to ask those deeper questions about fundamental features or fundamental properties of the universe from quantum theory. So, as Schrödinger said in his entanglement paper for the Cambridge Society in 1935, entanglement is not one, but the characteristic property that causes departure from classical theories. So entanglement is quantumness in essence. And there are some theoretical work or proposed experiments that use indefinite causal ordering to understand or probe entanglement in various situations. So that's very cool. So we might be able to use indefinite causal ordering to shed some light on these old questions about the properties, the underlying properties of the world from quantum mechanics. We might also use it in our future theorizing, not just to understand quantum mechanics per se, but maybe we can look at the lack of causal ordering as motivating certain efforts to quantize general relativity or to quantize gravity over others. And so I'll have more to say about that in the future. So a lot of responses from the physics as well, and we'll zoom in on a few of these that will feed, I hope, into a metaphysical type thesis. So plan of the talk, pretty typical philosophy of physics sort of talk. I'm going to start by looking at some of the physics, right? I'll ask I'll look at three things here. First, I'll briefly discuss, since this is an interdisciplinary audience, why would we expect indefinite causal ordering in quantum processes in the first place? And once we've covered that ground, I'll look at a particular experimental case, the quantum switch. And the quantum switch is a way of measuring degrees of non-causal correlation, right, among processes. So it's very cool. And then I'll look at a relativistic case. So this is an experiment, a theoretical experiment presented by Henderson, she's at, I think, Waterloo, and co-workers. And they're looking at how...
Please, I have a quick question.
Sure.
Is there a reason you are using the word process rather than events?
Yes.
Okay.
And that will become a little bit clearer when we get into the details of the quantum switch. But
thank you. Yeah, thank
you. So Henderson and her colleagues have been looking at quantum field theory, entangling detectors that are coupled to the field and using it to harvest entanglement. And they've found some preliminary, very interesting, both more efficacious ways of coupling detectors in a non-causal superposition. They can harvest more entanglement with that kind of superposition among their detectors. And also they raise some very interesting questions about, well, what does it really mean to have the detectors, which are physical things, presumably, in superpositions that are physical states, presumably, that nevertheless yield these strange sort of backwards, forwards superpositions. Okay. So look at the physics first, and then the second part will be just sort of drawing out some of the consequences of this physics. And this is the part where I'm doing totally new stuff here with you all now, and so I'd love to have lots of discussion with you all about it. So again, I'll sort of look at the quantum switch and what it might imply or not imply about causation in quantum physics, and then I'll look at the case of entanglement harvesting in QFT, and sort of have a think about what that might mean. And then part three is very quick. It's just where I'm going to make some talk-sized theses, right? The specific talk-sized thesis about causality in quantum theories. What can we say given ICO as an active area of theoretical and experimental research right now? What can we conclude about causality in quantum, but also maybe in physics more generally? Maybe, right? And then a general thesis, which isn't about physics alone, but is back to that question I started with about the metaphysics of causation itself. Has any of the physics that I go through, has it modified or made easier or more difficult certain aspects or defenses for those three main approaches to the metaphysics of causation, the Humean non-fundamentalist account, the non-Humean sort of fundamentalist account, and then the Limitivists. Right. Okay, here we go. So the physics, so the question, why do we expect indefinite causal ordering in quantum processes in the first place? Well, in the literature, and I think there's some care that needs to be taken from philosophers here too. Because in the literature, it's very quickly said by the physicists that there are sort of these two reasons that come from the formalism of quantum mechanics that lead us to expect uncertainty with respect to everything, including causal properties, but maybe also the experimental violation of Bell inequalities tells us also something about causality. But as I note 2/3 of the way down the page there may be different notions of non-classical causal structure being implied by these different things. So keep that in mind. So here's the theory reason number one. It's just the superposition principle, right? We do quantum mechanics in Hilbert space, and one of the properties of Hilbert space is the superposition principle, namely if psi1 is a solution, a possible state for some system, or a process that systems can undergo, and psi2 is likewise a solution, an event, process, then any linear combination of them is also a solution. So you've probably heard this described in the double slit experiment. If passage of an electron or a photon through one slit is a possible solution, it is, and passage through the other slit is a possible solution, it is, then a superposition of passage through slit 1 and slit 2 is also a possible solution, a possible state that the electron could have, or the photon, right? So what this means for causal processes is that it's possible that there's a state, but state here is broader than state before because it characterizes not an event, but a process, right? Resulting from two ordered simple operations. So you could have a process where operation A happens first, then operation B happens, and that process is in a superposition with the process where B happens first and then A. Now notice I've left it vague in this setup whether there's a causal relationship between A and B or whether it's just a temporal relationship. And that will make a difference when we get to the entanglement harvesting quantum field theory work by Henderson and colleagues. Okay. So prima facie, the superposition principle would suggest that superpositions of processes are possible in the same way that superpositions of states are possible. Theoretical reason number two is the uncertainty principle, Heisenberg's uncertainty principle, that there's a bound on the precision with which canonical variables can be, commuting variables rather, can be simultaneously measured. The question that many of the physicists begin their paper with who are doing ICO is, well, if there's uncertainty regarding classical properties like position and momentum and velocity, then it stands to reason that causality, which is sort of a meta relation, a relation that comes out of the relative space and time and momentum and velocity of the systems in question, then surely there's uncertainty at that level as well. And here's my little nota bene. Maybe there's a different kind of uncertainty that arises due to causal superpositions. A superposition of one causal ordering with a superposition of another causal ordering that seems to be a different state of affairs than just saying that there's indefiniteness or that there's uncertainty in some causal process. Okay. So, right. Hi, Kat, are you weighing in? Good. The experimental reason for expecting indefinite causal ordering in quantum processes is just ye old Bell's inequalities, right? If you have an EPR pair of entangled particles and you send them shooting off in some different directions, you have spatially separated detectors. And you measure sort of the correlation between, polarization of those photons. And you look at the statistics, the amount of times they agree or disagree. Classical probability gives you some upper bound of how often you would expect them to agree when you set the detectors to different angles and so on. Bell's inequality says, look, if there's a correlation greater than this amount, then it just can't be described by classical processes, right? So there's already causal notions packed into the Bell inequality. And as many of you are well aware, interpreting what Bell tests mean about locality or separability or entanglement or causation has not only spawned new interpretations of quantum mechanics, but spawned a robust literature. So it's a complex question, but the very rough idea that Bell's theorem provides a bound on what a local theory should be able to describe versus what a non-local theory would give rise to is sort of considered by many ICO physicists to be analogous to what they're trying to do. They want to find bounds that tell them whether processes are existing in causal or non-causal orders. Okay. So a little bit of the background here, the basic theory of a quantum switch. And so just if you don't remember, quantum qubit is just a two-state quantum system. So like a spin half particle or something. So imagine we got two qubit state, and the two qubit state, composite state, capital psi, where you've got a control qubit C and a target qubit phi t, and they live in a joint Hilbert space. All that's pretty normal quantum mechanics. But now we can set up a scenario where we condition two different operations, operation A, which could just be a measurement in a lab, and operation B, and apply them to our target state. So depending on what value the control state has, the target state will be operated on in a different order. So we might categorize this down here as bottom. That if the control state is at value 0, right, or in state 0 or spin up, if you will, then we're going to perform the operation A first, then B on our target qubit. But if the control qubit is in, I don't know, the other states, so spin down maybe, then we're going to perform the operations in the reverse order on our target qubit. So we just went through the superposition principle. Should be pretty obvious that if the control qubit is able to be in 0 or 1, then it follows that it's possible that it's in a superposition of 0 and 1, right? Maybe a maximal, like a nice superposition right here. And what results from this is a superposition of operations. So you have the process, first A, then B, in a superposition with the process, first B, then A. And note that this superposition of processes is itself, right, a superposition, but also is itself entangled with the control qubit state. So it's non-separable already. So this really interesting little image, but I think it's helpful, is from Rubino et al. And Rubino and his colleagues were the first, as far as I know, to experimentally directly verify the existence of indefinite causal ordering. And so here we've got our process matrix at the bottom, W. Ooh, I don't have a point. Can you see my pointer? Well,
yes, I believe so, Elise.
You can?
Mm-hmm.
Okay.
Yes.
All right. So at the bottom of each of these three panes, which are three different scenarios, we have the W, the process matrix W, which tells us what the path was, what the order was for the target qubit. So here's where we're saying the control qubit is in state 0 or spin up, if you wish. In which case, the target qubit is we'll say that this is Alice. Alice is in her independent lab in England, and she does a measurement on the target qubit and then sends it over to Bob. And Bob is in Istanbul, and Bob does the measurement, and he performs process P on it, and then we get an output, right? It could go the other direction as well, where the first Bob gets the target qubit and then Alice does. And then this final state is the one of interest for the quantum switch, which is when we have the control qubit in a superposition of those processes, in which case the target qubit performs a superposition of both of the prior processes, right? So it's unclear what ordering, causal ordering, is going on between Alice and Bob. It's not predetermined by the setup. I'll say that a little more about that in a moment. So another way to characterize this, the quantum switch, in a quantum switch, we've got W. The particular ordering is it first does this process A here. It goes the other direction. It first puts the input state through a superposition of A and B, and that gives us some output 1 parentheses. Then it sends the input through A, then B, which results in output 2, and then through B, then A, resulting in output 3, and then it coherently recombines all of those outputs. And that measurement is the measurement we're interested in. It will tell us what degree, if any, of non-causal ordering was evident between the processes, A to B, then B to A. So in order to understand, to make this measurement or quantify the degree of entanglement or non-separability between these causal states or causal processes, forgive me, the physicists build a causal witness, which is an operator that's supposed to be analogous to an entanglement witness. So just in case you don't know, entanglement witness is just a Hermitian operator that when it acts on some composite system will give you a density matrix when you carry out the trace of that composite system with the operator acting on it. If the trace is less than 0, you can conclude that the subsystems are entangled. And to what degree, and if the trace is greater than or equal to 0, then you conclude that the composite system was separable. So analogously, but instead of using a density matrix, here we want to use the process matrix W. And so here's the difference between a density matrix and states, right? With a process matrix W and processes. So a causal witness then is just a uniquely, specially defined Hermitian operator that acts on the process matrix W, and which describes the state of the operations. And again, it yields a trace of less than 0 if the processes it's witnessing are causally separable. So we can say that A then B happened first, then B then A happened, or vice versa. But the measure is greater than or equal to 0 if they're entangled. And I believe it is flipped like that. Like, so it's less than 0 if they're separable, and greater than or equal to 0 if they're entangled. And so, of course, much like with the Bell inequalities, you can come up with sort of this upper bound or with these limitations for what you expect for degrees of entanglement between these causal processes. And the experimental agreement is high. So just to back up a little bit, and maybe put this in slightly more layman's terms, I suppose, Oreshkov and his colleagues in 2012 sort of gave a theoretical picture of what this process matrix might be like. And they assume that there's this game between Alice and Bob. I mean, Bob has some strategy where he's going to get his system, he's going to receive it from Alice. And if what he receives from Alice is a particular state, then he's going to do a particular kind of measurement. And if it's a different kind of state, then he'll do a different kind of measurement. So his output is conditional on Alice's, and so on. So there's a causal connection between what Bob does, the measurement he does, and what Alice is doing over in her lab. And so Oreshkov and his colleagues calculate that if you assume that there's a causal order, that it's very clear that Alice sends her state to Bob, he does his measurement, and he's successful, conditional on the input of Alice's lab. They say that the success will be less than 3/4 of the time he's going to be able to implement a strategy that is successful. Okay. However, if they set up this, again, it's like the superposition of the causal ordering in the quantum switch, right? If Alice and Bob, the order that they receive each other's information or states is not determined beforehand. So it's not that Alice sends a result to Bob and Bob makes a conditional decision. If it's indeterminate, then in fact, Bob's rate of success at adjusting his measurement based on what he receives as input from Alice is higher. This is exciting because at least for Eshkov and others, it shows that perhaps if you do have indefinite causal ordering between these two operations, you can get a higher efficiency. You can get a success rate for certain computations that's higher than if you're dealing with causally ordered sets of operations. And that was in fact what was proven in Procopio et al. 2013. So they indirectly verified the indefinite causal ordering of a quantum switch. So they didn't use a causal witness. So they didn't get an exact measure on the entanglement, but what they did was they showed that they could get higher efficiency on some computation when using a quantum circuit that was in a causal superposition, as opposed to a circuit that was in a causally ordered, in its processes. So the teams listed below said, okay, well, we want to do one better. We want to implement this causal witness schema and see if we can directly verify indefinite causal ordering. Because in a sense, what Procopio et al. Had done is just to show that the superposition was more effective than sort of separable causal ordering. But they wanted to get Rubin et al. And Goswami et al. Wanted to get quantitative about it. So they developed the causal witness, and they did in fact measure values that were in close agreement with the theoretical expectation for non-separable causal processes. So upshot here, these direct verifications of indefinite causal ordering are showing are measurements of entangled causal processes, of processes where order A and B is entangled with B and A, and so on. Pretty bizarre. I would like now to talk briefly about what might be happening in quantum field theory. And as far as I'm aware, a lot of this work stems from something Bruckner said in a 2014 paper, which was sort of a review of the field, physics and causality right now. So he made this interesting suggestion after describing the quantum switch, saying, well, look, we could probably do something analogous using a massive object that's in a superposition of positions. Because if they're spatially separated, like the component states have some spatial separation that they're entangled over, that means that the gravitational field that that massive object produces will also be in a superposition of states, ergo, the space-time geometry itself will be in a superposition. And so I have this quote from him here, that the causal succession of gate operations in a quantum circuit or a quantum switch is the analog of events separated by a time-like interval. This analogy can be pushed further. The networks in which geometry of the wires between the gates is entangled with the state of the control qubit, so again, the quantum switch situation, can be thought of as a toy model for the quantum gravity situation that he introduced before. Namely, if you put a massive object in a spatial superposition, then the metric that's produced and the spatiotemporal distances between the events in the gravitational field get entangled with the object's position. So this suggests new ways to understand entanglement at different locations in a field, and also to possibly motivate or constrain the ways we quantize general relativity. So to that end, very recently, here's the Henderson et al. Paper that I mentioned earlier, quantum temporal superposition, the case from QFT. I'm going to be really brief on this because I want to get to the philosophy. Quantum field theories describe correlations between space-time points. That's what they do. So if we put like a really tiny little, like a quantum system that's a particle detector in the field, and we couple it to the field, then it can perform measurements on the field and can tell us about local values, it can tell us about correlations and so on. So these physicists asked the question, okay, and you notice Bruckner is among the colleagues here. So maybe he made that 2014 suggestion with malice aforethought. But question, what if we put two particle detectors out in the field that are in a quantum superposition and then use that, that composite or superposed detectors, use it to probe field correlations? Another way to say that is in particular to harvest entanglement, to measure degrees of correlation, quantum correlation in the field. Will we, in analogy with a quantum switch, find higher efficacy when the detectors are in superposed states? Will they be able to measure a higher degree of more effectively measure entanglement, rather? And it looks like that is in fact the case. So they looked at two different situations here. So they took, so on the left-hand side here, they have two different detectors that are in a cause-effect superposition. So it's an explicit superposition where A will cause some later state B in detector B, and B causes A, right? Whereas on the right side, it's just a past future. So it's just a temporal ordering, A before B, that is the time that the detector takes a measurement, A before B, and then B before A. They found some weird, first of all, like that they could propose this theoretically is quite something, because there are no-go theorems about how the signaling among the superposed detectors can work and so on. It's quite a feat. But it's interesting because they found out that in each, like in the left-hand case and the right-hand case in this image, you have a branch, you have different branches of the superposition. And while you can transform one branch either from a cause-effect superposition to, from a cause-effect situation to a past future, you cannot ever do that so that both branches agree in cause-effect, whether they're cause-effect relations or past future relations. So there's sort of that interesting way that it looks like they're able to tell by coupling these detectors in the right way with the field and they're being in a superposition with one another, they can differentiate between superpositions that are just A before B and B before A versus legitimate superpositions of A causes B with B causes A. So one of my worries earlier on was that, well, just because they're indefinitely causally ordered, or even in a is not necessarily the same thing as being in a superposition of A causes B just as much as B causes A, if you will. But this proposed experiment does seem to be able to discriminate between what I might call a genuine superposition of causal processes. And that's truly weird. On the efficacy front, they do find that that putting detectors in superpositions in this way allows them to be more effective, to more effectively perform entanglement harvesting. So just as with the quantum circuit, it was found that a superposition of causal states was more effective for a certain computation. Here they're finding that entanglement harvesting, or just the probing of the field for different correlations, is more effective when you're dealing with superposition of detectors as opposed to pure states of detectors. Okay, that's the physics. It's all pretty brand spanking new. What can we say about it? Here are some things I was thinking about. If we think about the proposal made by some of the physicists that causality might be just another aspect of the uncertainty relations, it's uncertain because causality is ultimately redefined in terms of variables at the lower level, and those variables are susceptible to uncertainty because of quantum mechanics, right? Okay, maybe. But that doesn't seem to be what the quantum switch or the superpositions of particle detectors in a quantum field are seeing. It's not that they're seeing uncertainty in the ordering of processes. It's that they're measuring superpositions of well-defined causal processes. So I'm not sure that what benefit it might be to think about causality as analogous to uncertain properties like position, momentum, velocity, and so on. A further problem is that the interpretation of the uncertainty relations is somewhat debatable. I mean, there are limits on whether you can assign well-defined values to a system before before measurement, and those limits are described by, for instance, the Koch-Specker theorem. But there are ways that you might recover a sort of epistemic or operational understanding of uncertainty, where it has to do not with the nature of the world itself. The world itself is just defined perfectly clearly. All the states are definite states and so on. And it's just that by doing a quantum, a measurement on a quantum system, we introduce disturbances of a kind that lead to uncertainty in various properties of the system. But I wonder if there's room to make sort of a more metaphysical or ontological claim here, that if you do understand the uncertainty relations as saying something about the way the world is and not just how we measure the world, or if you understand the way we measure the world to be a part of the way the world is, maybe measurement just is defined as weakly as an interaction, any sort of interaction. Interactions are happening all the time, all over the place. What is the nature of those interactions? I'm not sure how we would ever determine whether ICO makes legitimate an interpretation of causality as fuzzy or as uncertain in this way, but I want to think more about it. What seems more plausible, and in fact, quantitatively plausible as well, is that we might be able to come up with theorems for measuring or gauging the quantumness of relationships between systems. And quantum correlations I tend to read as entanglement. I think that's what's meant by quantum correlations, entanglement. So in this way, we can use these bounds on causality to understand more about entanglement relations among different kinds of systems, just in the same way that we've measured spatial entanglement using Bell tests, or maybe the way that we look at temporal correlations and gauge the quantumness of various system or of a system through time using Leggett-Garg inequalities. So it's been proposed by, I think Bruckner was one of these physicists, that it looks like causality, that a process and not just the spatial temporal location of events, but that a series of events might also have bounds that describe entanglement thresholds, as it were. There's a further question which I want to explore, which is whether causality is recoverable in causally neutral formulations of QM. So these causally neutral formulations do exist, they're out there, but whether they're realizable in some way, and whether the kind of causality, the notion of causality that is recoverable from them is, well, what kind is it? Is it merely a descriptive kind of causality? Is it a loose ordering of events where you have certain probability bounds, like conditional probabilities, that given this event, the probability that this other event happened prior to it is such and such? Okay. Whether those are the kinds of causal notions that emerge from causally neutral formulations of quantum theory, or whether it is some robust sense of causality, that there's really, as Norton would put it, sort of a factual constraint that's being imposed upon the systems we're measuring that is causal in nature, yet doesn't exist at the very bottom level where we have indefinite causal ordering. And then the last sort of physicsy speculative point, which I won't go into, is there, just as Bell's inequalities and perhaps Leggett-Garg inequalities, but to a lesser extent, but certainly Bell's inequalities carved up the interpretation space for non-relativistic quantum mechanics in a very different sort of way, right? It made more clear the goal of a de Broglie-Bohm contextual hidden variables theory. This is what the theory needed to do to recover empirical data, yet account for causality, because de Broglie-Bohm, they want to have sort of classical processes in the background, or recover classical processes at the level of, I don't know, the universe, maybe. Right. So maybe in the same way, if we come up with causality inequalities based on indefinite causal ordering, that will shed some light on or recarve up the interpretation space in an interesting way. But I suspect that the right move is not to recarve up the space, but in fact, oh, this is a general conclusion, but I'll go to it now. No, I won't. Hold on, just keep it in mind. I suspect that it's just more impetus for ditching causality as a fundamental aspect of our interpretation of the world in the first place. So if you've built, as some Bohmians, for instance, sorry, I'm picking on Bohmians today, most days, if the Bohmians have expressed, like, their motivation for developing their pilot wave theory or their contextual hidden variables theory was to recover at the macro scale classical behavior, right? They want their systems tracing out quasi-Newtonian trajectories, right? They want the world particle to be moving deterministically. That means that the prior state is a cause for the later state, and so on. So a large motivation for that interpretation is to recover classical notions, among them causality, arguably, in which case, maybe this is just another reason to sort of avoid that interpretation. Okay. Another point to make very quickly is that a lot of discussion about relativistic causality in physics, and as far as I know in the philosophical literature, has focused on signaling and the bounds placed on signaling by no signaling theorems and so on. But I think that these ICO processes and like the Henderson et al. Detectors and superpositions in the field, I think these are methods of understanding or of approaching the question of relativistic causality that are not primarily about signaling. So it might be just a different avenue for thinking about relativistic causality, broadly speaking. How are we on time? Oh, fantastic. I shall now wrap up. I've already mentioned some of the relativistic consequences, namely that it gives us more specific details about it gives us larger regions for entanglement harvesting. So we just learn more about the quantum field when we couple it to superposed detectors in this way. But we also asked the question, and I heard Henderson in a talk she gave, like she ended the talk by saying, it looks like we're dealing with physically superposed detectors that have a real effect on the probing of entanglement. What does this mean? What does this mean for how we construct future quantized theories? What is the, I think she was asking, what is the metaphysics of this, right? Well, let's figure it out. I've mentioned also that it motivates attempts to develop a theory of quantum gravity or any kind of quantum theory that is background independent. So it doesn't assume going in that there's a set space-time manifold or that there's causal structure embedded in the background. Okay, so maybe that was, I didn't finish editing that point, but go on to 3. Look down at 3. Don't pay attention to 2. Oreshkov and others have suggested that if causality like spacetime should be considered dynamically emergent, I mean, what we see at the macro scale as clear causal connections do not exist in that definite way at the micro level, then perhaps we can start building up a story about the emergence of those more concrete or more classical causal structures. And maybe I suggest those are dynamical stories that involve, for instance, quantum decoherence processes, which can effectively damp those superpositions so that even though they are physically superpositions, they nevertheless are only measurable by some other probe, by an environment, by us, by a lab, by Alice, by Bob, as being effectively an eigenstate, right? So not in a superposition. And it might even support like canonical approaches to quantum gravity over covariant approaches, because canonical approaches, because the Wheeler-DeWitt equation doesn't evolve in time has to come from somewhere. And there's some work, like Moravia et al. Has this interesting paper where he and his team derive, say that even if you have a static macro system or composite system, if you carve it up into subsystems that are entangled with each other in the right sort of way, they can be evolving in time and you still have a composite state that is static. Well, that's exactly the sort of thing you want for a canonical approach to quantum gravity where the Wheeler-DeWitt equation is not evolving in time. But again, this it's possible that a project like Moravius that has to do with recovering time from entanglement is possible in terms of causal processes as emergent from entanglement in that way. Okay, so the specific thesis, just it seems that this physics, just the fact that there are a lot of people studying indefinite causal processes in a variety of ways, and not just operationally, but as what it could tell us about fundamental features of the world, like entanglement in quantum field theory, that causality either just isn't a part of the world at the lower level, or if it is, it's indefinite, but we should become clear about in what sense it's indefinite, and if there are bounds on how definite it is or indefinite it is. And given that, we do use cause at higher levels. What is the nature of these causal processes, given that there's clear evidence that if they are emergent, which they probably are, how does that emergence process happen, right? There's nothing causal at the fundamental level, whence cause at this higher level. Right. And then, of course, looking at the relativistic case of Henderson et al., we can understand more about entanglement in relativistic scenarios by studying, using indefinite causal ordering as a tool to probe. So it's not just that we've measured indefinite causal ordering, it's that we're now using indefinite causal ordering to understand other parts of the physical universe. That's pretty cool. Ending where I began, if we look at the three major camps for metaphysics of causation, it looks like causal fundamentalists have an even harder task given ICO. So for instance, the Bohmians often say that we require a primitive ontology that has a law that's causally a causal law, and the Bohmian world particle evolves according to that causal law. That seems less attractive to me, given ICO and sort of all this active research. The Limitivists, there could be serious problems too, because if causal talk, like Norton wants, is only allowed in virtue of its being ultimately reducible to some non-causal microtheory, well, what if it's not just there's no cause down there, and it's but that it's sort of entangled causal processes? There have been arguments already in the non-relativistic literature that you can't have reduction onto a base that's entangled, because entanglement is sort of a holistic property, right? Entanglement relations cannot be further reduced because the parts are something different than the whole. Hello. And then finally, I think this comes out on top for the non-fundamentalists. They seem to be safe on their claim that causality does not exist in the fundamental makeup of the universe, but it seems like we still have important uses for recovering causal processes or causal models, like the quantum Markovian causal processes at the higher level, quantum Markovian models, rather. But I think the task may have become slightly harder given ICO, because there's maybe a larger gap between the fundamental level and where it is that causality comes in and is useful to our modeling processes. Okay, it's a lot, very speculative. Can't wait to have a discussion with you. Here are very brief references. Thank you very much.
Thank you so much, Elise, for this wonderful talk. Much to think about. And before I open up the floor for questions, I wanted to acknowledge the fact that, we're delighted, Elise, that you are part of our core team for this project. So excited to have you part of the organizing team to help us understand. And I also want to give a shout out. We have in the audience, we have Lorenzo Magnani, who was one of our previous speakers, who is dialed in from Italy. And we have the person who I consider my guru in quantum mechanics, whose book I learned from, Ramamurthy Shankar, is in the audience. And we also have Peter Morgan, who is thinking about these issues, who is in the audience. So as well as, Chris Mink. So yeah, you've drawn quite the crowd, Professor Krull. So, so I think And I also have greetings from Canada for you. So you've had fans across the globe. So I think I want to start with one question that one of our, again, a regular attendee, Sanjeev Kumar, has. And it's really a question he has about classification. So in the consciousness-only ontology, the non-causal substrate of consciousness becomes compatible with temporal causation. Actually, I'm not sure how that is, but that's a big claim, right? Does your framework tie with the consciousness-only ontology? You knew this was coming, right? A question about the big...
consciousness?
Yes.
Well, I'm about to shock you all. Hang on to your chairs. I take it that the consciousness only view, which I'm not super familiar with, but it's still a physicalist view, yes?
Yes.
I'm not a physicalist. So I really can't answer that question because for me, consciousness will not be ultimately describable in physical terms. And so whether or not the physics that we do have can adequately recover temporal, spatial, causal notions is a very different question for me. Yeah, so that's a very short answer to a very complex question, but right. I think, in fact, if there's anything that can be said here at all, if it's that causation's being less likely to sit at the fundamental level, could be used in various ways by folks arguing for consciousness from quantum systems, right? It depends on your end game. If causality is supposed to be a feature of our noetic structure, right, then the fact that it's not at the quantum level is maybe not so much of a problem. But if all there is consciousness, but there isn't causality at that fundamental level, then you're going to have to do maybe a lot more legwork to sort of explain whence sort of this conscious awareness of causality that seems so natural to us in all the sciences and not just in physics. But yeah, I'm really out of my depth talking about consciousness to physicalists. So,
so I guess I have something that has sort of confused me. One of the many things that is complex and confusing. So are you making a distinction between entanglement being an intrinsic property versus an emergent property? Or am I really confusing by saying that you cannot reduce it? Is that what you're saying?
So I'm thinking not in a temporal sense, but in the metaphysics sense, that you might, if you want to give a totally, if you want to reduce the whole world to bits and bops that are quanta, but these quanta exist in entanglement relations, that means that my quantum system over here, its properties are not fully described by the spatial temporal region I carve out that contains, I don't know, even the majority of the mass of that object, right? If it's entangled, it may have properties that are spatially, temporally extended.
Right.
That's all I meant by that. So it's not
non-local, sort of the non-local nature. I see.
Yes. Yeah. So it has to do with non-local. Absolutely. Yeah.
Okay. Mm-hmm. Any other questions? Yamima, if you feel free to ask questions today as well. We would really greatly benefit by anyone asking thoughtful questions.
Hey, Priya, can I jump in here?
Yes, yes, Shankar, please do.
So I think the subject is very difficult, but I do feel that if somebody could explain it to me, it is our speaker today. Because I could follow the part that I knew, I could see how well it is explained, but that lots of it I don't know. I'm just a Copenhagen hack. I sort of know the standard way to do it. In my world, the measuring instruments are of a different size from the measured objects, and a very clear distinction between the macroscopic world needed to define measurements. I think in this study, you're reaching a domain where they get blurred, where they get small. Yeah. So they're issues I've never thought about. But as I said, if I want to learn what these issues are, this was a very good introduction. So I got to thank her, Elise, for doing that.
I'm really honored. Can I ask you a question while I've got you?
Yes, I was just going to say.
As a philosopher of physics, it may not be the one you want, but as a philosopher, I'm a student of Don Howard's, who was famous, among other things, for writing about the myth of the Copenhagen interpretation, sort of historically. It was an interpretation Heisenberg came up with after World War II that aligned him more closely with Bohr. Bohr emerged from World War II as a hero, advocating glasnost and meeting with Churchill. And, well, he did work on the Manhattan Project, but he was, I don't know, careful about it. He was very conscientious. Heisenberg did not emerge from World War II with a similar reputation. And so it was, he made it up. Okay, so if you historically study Heisenberg's view and Pauli's view and Jordan's view and Einstein's view and Schrodinger's view in the period 1926 to 1935, which I have a book coming out on that, they have very rich and very nuanced different views. So here's my question. Many physicists I encounter still claim to be Copenhagen people, but what does Copenhagen mean for you? That there's a distinct classical realm, or that measurement processes produce truly definite outcomes, not just apparently or effectively definite outcomes?
Yeah, I imagine a world, look, you got experiments going on all the time in CERN, they're measuring particles. That's a probability distribution for where the particle will land.
Right.
And if a detector is placed at that angle and you vary the angle, that's a function that's predicted. And that seems to work. We seem to know what we mean when we measure the pion in this detector. That's the level at which I understand quantum mechanics, the level at which it works.
Okay.
But their detectors are huge. In fact, particle theory experimentalists never fail to show you how big they are compared to a human being. All their pictures have a huge detector and a tiny person standing next to them. In that world, the problems you say will not arise. You can never put two of those big guys in a superposed state.
Right.
So I don't have the issues you're raising. These are issues you have to deal with the issues before they come and ruin your life. But at the moment, I'm almost finished with my career, so I'm not worried about what will happen 15 years from now. But these could be dominant issues.
Yeah, and so, I mean, this is brand new stuff for me. What I have mostly done, aside from the historical and foundational work, is decoherence studies, and looked at sort of that. And so it does seem clear that, at least in principle, there is no well-defined domain. I mean, even if you take the usual limiting theorems like Ehrenfest's theorem or the Liouville regime or whatever, like none of these gives a universal description or universal classification that slices the world where you get just classical systems on one side and quantum on the other, whatever these may be. You always have problems. And so let's just let everything be quantum. And then let the dynamics of quantum processes like decoherence tell us why we see effectively classical states at large, like mesoscopic and macroscopic scales.
Right. And there are also people at Yale, like Jack Harris, who are flirting with the dividing line between classical and quantum. They got mechanical objects, which are, I think, the largest one in which you can see superposition. So they are cantilever oscillators, which can be in a superposed state.
Right.
It's a big enough thing that you could probably see in a microscope, but yet it is really in a superposed state. But I thought everyone agrees that that is challenging, but it's going to be a long way from getting anything substantial in a superposed state. So.
And that's partly the game too, right? Because this is clearly a problem for quantum computing, where you want to shield you want to maintain the integrity of your qubits. You can only do that by maintaining coherence, but decoherence is so damned effective and so fast that this is a real engineering problem. But if we're concerned with if we're interested in the metaphysics, right, the fact that we're trying to shield systems from losing this property indicates something about the way nature prefers it, as it were, in sort of this quantum entangled situation. Yeah.
Yes, I agree. I think I shouldn't monopolize your time. So thanks for taking my comment, and maybe I should let other people talk to you.
Thank you.
Shankar.
Okay, going to mute myself.
Yeah. So I think, Peter, did you have a question, or did you just want to give that shout out? I guess
Just a shout
I
out.
think. You want me to ask something?
just a shout out. Yeah. Yamima, please go ahead. Yeah.
Yeah, so just to, first of all, thanks, fascinating description of all these new developments. And we can talk about the metaphysics or what is causation tomorrow. But I was just thinking about backwards causation or retro causation. And you could understand what you described, or certainly entanglement. There were ideas about explaining entanglement in terms of retrocausality. And what you said, you never mentioned the term, but what you said seems to be compatible with that in some cases. So what is a connection between what you said and what those interpreters of quantum mechanics who accept retrocausation as an explanation?
Well, Yamima, thanks. I hope that's something we can talk about at more length tomorrow. And that's, I sort of intentionally left it out today. I waved at it from a distance when I talked about the different, like maybe that there's some, there's a lack of clarity about whether we're talking about causal processes that are causally ordered and it's just unclear, versus a superposition of a legitimate A caused B, but then B caused A. And retrocausality would only really apply to part of one of those situations. And so in a sense, if we can sort out what a superposition of causal processes really means, that will illuminate how much overlap, if any, there is with the retrocausal literature. But retrocausality, so one of the figures, historical figures I've done a lot of work on is Greta Germain, who wrote like the greatest and maybe the first philosophical treatise on quantum mechanics in 1935. And she's a Kantian, so she wants to preserve a fundamental causal principle. But she does this by first teasing apart, as you well know, Yamima, and as you do so nicely in the introduction to your book, determination and prediction as a separate thing, and the existence of a chain of cause and effect. And there is a chain of cause and effect, she says, in quantum mechanics. We just cannot know it beforehand. We can know it retrodictively. So it's not retrocausality, but sort of retrodiction of something that already existed in the world, is sort of her way of maintaining the causal completeness of quantum mechanics. But yeah, I know Hugh Price and others have done really interesting work on retrocausality. And if retrocausal theses still require a particular causal ordering of events, it's just not in the order we are used to or experience, that's a different thing than saying that it's a 1 over square root 2 superposition of A caused B and B caused A. Like, what does that mean? So I hope we can talk about that more tomorrow, and you could teach me some things about retrocausality.
Yeah. Great. So I just wanted to read out a couple of shout outs before moving on to the next question. So Lorenzo Magnani said, has provided a reference on some ideas about physics of consciousness. He refers to the area of studies called the so-called dissipative brain. For example, there's a chapter in a volume, Understanding Brain and Consciousness by Vitello. And he's given the reference for anyone who wants it in the chat. And Peter Morgan gave a shout out for Don Howard's 2004 paper, pointing out the difference between Bohr and Heisenberg on the nature of, that's a wonderful paper. And he's mentioning that it was formative for him. It was quite the paper to plow through, but it's excellent. So I think Firdaus has, who's another of our regular attendees and fellow astrophysicist, he has a very nice question, which is sort of where I was going next too, that he says, you mentioned decoherence and that your thesis work was based on it. Can you elaborate a little bit more on how this may have influenced your developing the ideas, for example, that you've presented today?
Sure. Decoherence is due to entanglement. So there's a deep mother-daughter relationship between entanglement and decoherence. And there's also a lot of there's a lot of philosophical interest, but also confusion about both of these properties. Well, excuse me, entanglement as a property that systems might have, and degrees of it, and as it evolves through time, and decoherence as a dynamical process. So I've been thinking for a long time about entanglement in that guise, how it gives rise to and how it's not evident at the meso and macro scale because of like a lot of puzzles having to do with entanglement, I think can be given explanations via decoherence. So that's the relationship between entanglement and decoherence. But also, of course, these questions have to do with the quantum to classical transition. And because I'm interested in talking to metaphysicians, I think they go by metaphysicians, but it ought to be metaphysicists. I'm interested in understanding ontology, but in a way where it captures our best physics, right? And our best physics says that there's no hard and fast way to carve up the universe into classical and quantum, or even individual or closed or isolated systems. You were talking about dissipation. Well, dissipation is a big problem, right? The fact that we can effectively deal with eigenstates, or that we effectively measure with pointers, you know, a particular value for our measurement outcome, that there is a quantum process underlying those classical phenomena was really something I wanted to understand. Now, causality is a little bit higher up because is sort of leaping a step, because I want to think a little bit, entanglement is a process across space and time. And if you think about, because we're in a 4D or more world, right? So when we talk about entanglement relations, even when we call it the measuring of spatial correlations in a Bell type experiment, we're in fact already doing causal entanglement because those detectors are at space-time locations. And so just getting clear about, I started to ask about the Leggett-Garg inequalities and what they really have to say about temporal correlations and how we define macro versus micro versus meso systems and so on. And from spatial correlations and temporal correlations came causality. And then also Priya asked me to give a talk on causality. So that's a long-winded answer to your question, but yeah, so I'm new to the causality, and that's one of the reasons I'm extraordinarily honored and excited to have Yemima have a conversation with us tomorrow, because she is an expert on causation in science and in physics, and will bring a lot more fruit from what I've said, I hope.
Yeah, no, and I think that, you know, thank you so much, because I think the thing that is confusing to a lot of us is this idea of determinism, causation, transparency of causes, chains of causation. All these things are really hard to kind of clearly parse out when we are trying to understand. You know, you look at a model and you're trying to figure out a chain of causation and what all you can infer from, you know, model, given the priors that have gone into constructing the model to start with, right? So yeah, that was, yeah, really looking forward to it. Are there any other questions from the floor? Let me just take a look at the chat to see if anything else has
I don't think anything else has come in, Priya.
Okay, great. So I think at this point, we should just then wrap up with looking forward to tomorrow's really wonderful discussion where we can learn more. Thank you, Elise, so much for a really, really nice talk. I mean, I'm sort of tempted to ask a question which I will pose to both of you tomorrow, which is, you know, what do you really make of the prospects, the claimed prospects for quantum computing? You know, and whether are we being extremely optimistic, or is that just a completely different functional realm? If you can get it to work, you get it to work. It doesn't matter if we don't understand how it works, right? So I guess we'll get to that tomorrow. Thank you everyone for attending. And I want to say a big thanks to Ty once again for helping with managing and arranging this entire series and this talk. And I want to thank Ryan from for helping us with the recording and making the talks available online. So thank you, everyone. Have a lovely evening and see you all tomorrow afternoon at the same time. So 3 p.m. EST. Bye.
Thank you.